So before the spring break, we started on hydraulic conductivity or permeability testing, and we started with constant head permeability test. And today we are going to do falling head permeability test. So before we move on, let's quickly review what the constant head test was about. So we started with a soil sample, a cylindrical soil sample or length L, and then we created two water reservoirs, one at upstream and one at downstream, that created a head difference H. The overflow of water we collected as a volume of water, capital Q, over time T. So the flow rate Q, in this case small q, comes out to be capital Q, which is the volume of water over which it was collected time T. Then the Darcy's law says Q is equal to KIA. So we are substituting small q to be capital Q divided by T, volume of water divided by time, the permeability that we want to determine, the hydraulic gradient, which is H, which is the head difference, divided by the length of the soil sample, times A, which is the cross-sectional area of the soil. And by rearranging, we get capital Q times L divided by A times H times T as the hydraulic conductivity equation, which is quite simple. And constant head test is suitable for soils, mostly granular soils, with K greater than 10 to negative 4 centimeter per second. So for falling head test, we are going to have a different sample that has a little bit more fines content, and we'll see what kind of permeability we get. So the falling head test apparatus is very similar to what we used in constant head test. We still have a cylindrical soil specimen, as we are seeing in this diagram. So we have this soil specimen here of length L, and its cross-sectional area is going to be capital A. Then we have one end of it, in this case the bottom of it, connected to a constant head water supply or water reservoir. So this is all water. Whatever overflows in the constant head test, we actually kept track of it, but in this test we don't have to. Then we saturate the soil specimen, and then we attach a burette or a standpipe to the top of the specimen, and we start with one water level and let it fall to a next water level H2. So the initial water level with respect to the datum, which is the downstream constant water head, is H1, and after some time T, which we'll record using a stopwatch, it drops to a height H2. And then for derivation purposes, we are going to consider a certain height H in between H1 and H2 at a time T, and during that small change in time, we are going to say that the head of water changes by dH. Okay? So in order to derive our equation, we are going to start by writing down expression for velocity of fall of water in the standpipe which is minus dH divided by dt, and the negative sign is because as time increases, head decreases. So the flow going in the soil, Q in, is going to be minus dH divided by dt times A, and flow coming out of the soil is going to be K times I times A, where I is head at time t divided by the length of the soil specimen times the cross-sectional area. Then the next step is for us to equate Q in equal to Q out, because whatever goes into a saturated soil needs to come out. So it simply becomes A minus dH dt, which is K H divided by L times A. Then we are going to rearrange this equation so we can integrate it. So we will integrate it from T1 equal to 0, the start of the test when the head was H1, to time T or T2 so H1 to H2 minus 1 over H dH. So note that at time t is equal to 0, our head was H1, and at time T2, or at the end of the test, our head was H2. So we will get T is AL divided by AK in 1 over HDH. Integration of that will be log to the base EH, minus sign is there, H1 to H2. So basically, because of that minus sign, we get to say that T is AL AK log H1 divided by H2. So and this is natural log. So if we want to convert that to log to the base 10 and find the permeability, we rearrange the equation. We get K AL divided by AT log to the base 10 H1 divided by H2, and to convert from natural log to base 10 we have to multiply this by 2.3. So this becomes our final equation for the falling head permeability test, which is also in your instructions. Okay, so let's do a quick example. As a recap, for the falling head test, the permeability equation was 2.3 AL divided by AT log to the base 10 H1 divided by H2, where small a is the cross-sectional area of the standpipe and capital A is the cross-sectional area of the sample. So let's see what information we have. It says the data from a falling head test on the silty clay include cross-sectional area of the soil specimen 80 square centimeters. So I think you'll agree with me that that should be capital A. Then length of the soil specimen is 10 centimeters, which is capital L. Initial head is given as basically H1. Final head after 15 minutes is 84 centimeters, which is H2. But that also tells us that T is 15 minutes. So that's going to be 900 seconds. And then internal diameter of the standpipe is 6 millimeters. So we can use that information to find the cross-sectional area of the standpipe, which is pi divided by 4. And to be consistent with units, I'm going to convert that into centimeters. And that gives us 0.283 square centimeters. And our task is to compute the hydraulic conductivity of this soil specimen. So let's substitute all these numbers. So small a is 0.283 square centimeters. The length is 10 centimeters, and we are going to divide it by the cross-sectional area of the specimen and the time t, which is 900 seconds, and then log to the base 10. It goes from 90 centimeters to 84 centimeters, and that comes out to be 2.71 times 10 to negative 6 centimeter per second. So as a reminder, the falling head test is generally suitable for soils with K or the permeability less than 10 to negative 4 centimeter per second. I have a suspicion that the soil we have picked is going to be on the cusp of that, but we'll find out when we actually do the test.